think what we need to do first is a little bit of review to make sure that you guys are staying up to speed on some of the important stuff. Because it's a little difficult to actually program a machine if you don't know the architecture of the machine that you're programming. So, let's build a little memory map here. So let's first of all start with data memory, or the data space, I guess it's really officially called. What's the first thing we're going to find at the lowest addresses of data space? Scott?
General purpose registers.
Right, we're going to find at addresses 00 to 1F, in that area right there, are general registers, or general purpose registers. Let's just call them GPRs. What now immediately follows that in memory, in data space? Mikhail?
What follows is the commands CBI, SBI, SBIS, SBIC, in and out.
Okay, well, what it really, in terms of what we're looking for here, is we have a remapping of the lowest parts of I/O space. They run in data space from 2.0 to 3F. So 2.0, I won't get these lined up, I know, but 3F. We have a remapping of low data space. Now the next piece of memory we have, which is going to start at 4.0, goes up to 5F. What is this particular data space? But this should actually say, instead of data here, this should say, what am I typing in? Wait for it. Okay. Why is it not working? There we go. This is of low I/O space. So what's at 4.0 here? I know you know, Scott. Let's see if anybody else knows. Yeah, and when? What is it? Don't hear anything. DeMullen, what is it?
Is it data space?
Well, this whole thing is data space. What happens in 4.0 to 5F specifically? So again, what is that? Samir, what is it?
I was also going to say data space.
Robert, what is it?
Professor.
Robert, what is it?
I'm looking at my notes. The only thing I know about that data space is that 5F is the status register. I didn't have anything else significant written down.
Okay, Peter? You have to talk up. Barely. Hermel?
Is it the input output?
What has to do with input output, but not specifically. Mohammed?
Professor, I was going to say input and output too.
Okay. Well, that's not too wrong, but what it really is, it's a remapping of the middle. I'm clicking there or not. I/O space. And whoever told me a while ago this is the status register, they're correct. Now we have 6.0, and we go all the way to FF in this space. This is still data space. What is it? Robert?
It's the extended I/O space.
Right. This is specifically where extended I/O space is. It's not really a remap of it because it doesn't exist in the I/O registers at all. So it is basically extended I/O space. The next thing we have is from 100 up to 8FF. What lives there, Patricia?
It's the internal SRAM.
Okay, so this is where the SRAM is. How much SRAM do we have on this machine? Ian Nguyen, how much SRAM do we have?
I don't know.
I can't hear you. You have to speak up.
I don't know.
Tumalin?
Is it 2K bytes?
Well, that sounds pretty good. So we'll put 2K down. Now, some of these, they say they're remaps. What are the I/O addresses that these remap? So this is data space on this line here. So if I click here and go, that's data space. Above it here, I want to put what the addresses are in I/O space. Where is this mapped in I/O space? Numar? Where is this mapped in I/O space?
Not sure, Professor.
Nicholas, where is that mapped in I/O space?
Oh, I'm not sure.
Mikhail, where is it in I/O space?
I don't think it is in there.
That's exactly the right answer. That's not mapped in I/O space, which means where is this going to be mapped in I/O space, Jay?
I don't recall where that is.
Basu, where is this mapped?
I don't remember, Professor.
Did you write it down?
I think I did.
Andrew, where is this mapped in I/O space?
0, 0 to 1F.
That's exactly right. Where is mid IO space? Robert?
20 to 3F.
So 3F is the other address of the status register when you're using IO space. Where is extended IO space in the IO addresses? Robert again?
It isn't in the IO addresses.
That's right. It doesn't exist right here. Neither does SRAM. Now, there was a special set of instructions we could use with this that we couldn't use with that. What are those 4 instructions? Mikhail?
CBI, SBI, SBIS, and SBIC.
Okay. What are the other 2 IO instructions that we can use in this space, anywhere in this space?
In and out.
Right. So in and out are usable throughout all of IO space, except you can't use them in the extended space because you can only use extended instructions here. There's no IO capable in here, even though it's IO space. So in the extended IO space, the register or the instructions we would tend to use there will be the LDs, LDSs, and the LDDs, as well as stores, store in SRAM, and store data. They will tend to be the ones we use in extended IO space. And we've been over this about 4 or 5 times already, and some of you are still kind of sticking your finger in your ear when I ask you a question. You should know these things. You can't program the device unless you know what where its registers are and what type of instructions you can use on them. So those of you that didn't know your answer, shame on you. Those of you that did, congratulations, you did very well. How big is the program counter? How many bits? And when?
Um, 328K.
I can't hear you. You have to speak up.
328K.
That's a lot of bits. Tumolin, how many bits are in the program counter?
I think it's 14 or 15.
Well, pick one.
I'm gonna go with 14.
Okay, what is 2 to the 14th, by the way?
$16K.
Right, but specific number is 16,384. No, 9484. So that's equal to 2 raised to the 14th. We've got a cat hat here somewhere. That's not it. But we have 332,768 bytes of memory. How's that work?
Oh, it's 15 then. 15 bits.
I don't know about that. The 14 sounds awfully correct. Dante?
It has one extra bit for storage or for address registers.
Okay, I need a little more focused answer than that. That's not wrong, but a little more focused. Who wants to tell me why I can address 32,768 bytes with only 16,384 addresses? Scott?
The instructions are all at least 16 bits long.
Right, the other way to say that is instructions are multiples 16 bits. So I take 2 16-bit entities, 1 16-bit entity, 3, 4. In our case, it's only 1 and 2 on our machine, but we never have to address bytes. We only address words, and so we only need half as many addresses. At the top of program flash, there is a second area of memory. What goes in that area? Peter, what goes in that area? I guess we lost Peter. Patricia, what goes in that area?
Sorry, my mic was off. The boot program on top.
Yeah, that's where the boot flash section is. What's the bottom section called?
The application program.
Yeah, that's right. The application flash section. And the actual ranges of them from here up through, on this machine, 3EFF is where the application program lives. And at 3F00 through 3FFF, we have any boot program that might be. And we have a boot program loaded in ours because when we bought the chip, it was already there. Otherwise, you have to program it in separately. And just as a curiosity, how much EEPROM does this machine have? Dante?
It has 1 kilobyte of EEPROM.
That's right. 1 KB. Okay. Again, good. Some of you not so good as the rest of you that didn't participate there. Since I can power my machine off, we have 3 types of memory, right? 3 basic types. We have SRAM, we have flash, and we have EEPROM. Which one of these lose their contents when we power the machine off? Andrew?
The SRAM.
Yeah, the SRAM loses its memory. So if these both keep their thing, what's the difference between the two? Why would I use flash? When would I use EEPROM? What's my reasoning for using one or the other? Miguel?
Is it because you will use flash because it has more memory, and EEPROM because you could erase the contents?
Well, I can erase flash. I just can't erase it from a program. So one of the key things here is, erasable from a program. The other flash is erasable, but it's only erasable by things running in the boot sector. But more importantly, this is where our programs live in this. They don't live in EEPROM. It's much smaller. It can contain data, but this is normally, I guess, what we would call it. I can't get it something typed there that you can see. Personalization data. So it's things that you might not know when you send the processor or application to a person, but when they plug it in, need to have it remember things like their IP address, passwords, certificates, any of the various things like that they might need. Whereas the flash contains programs. It also contains one other thing. What is that? I'm beginning to think some of you might not be studying. is where any data that's going to be put on a program's variables has to live. It's the only place where we can store those values that will persist across a boot. So if I define a variable called pi and I make it equal to 3.14159, somewhere I have to store the 3.14159 in a place that won't go away when I power it off. How does it ever get into the right place? I'm going to grab a program here. Remember this? That says copy the initialization data from flash into SRAM at the location where you defined wherever the data section should be. Two sections here, BSS and .data. What's the difference? Scott?
.bss is allocating space for uninitialized data. .data is for initialized data where you specify a value in the program.
Right. And very importantly, that initialization data for this guy will appear in the .hex file. However, there's absolutely nothing in the .hex file about this. We just compute where it is and use those computations. The data that's going to be stored had to be burned to the chip somehow, so it's put in the data section. Now, how do we, in our code, how do we handle the BSS? What do we do to it? I'll give you a clue. I'll put my cursor and highlight what we do to it, and then you see if you can find it. Yanwen, what does this do? You have to speak up. We can't hear you. Sargon, what does this do?
I'm sorry. It clears
Clears what?
BSS.
And what is the BSS? It's your initials backwards.
That is the uninitialized data.
Right, it's where the uninitialized data is. Instead of leaving it just wildly uninitialized, we're setting it to zeros. We wouldn't have to do that, but we do. That way, even if we don't depend on it, it makes it a little cleaner. Okay. Why is register 0 always set to 0? I should add a bunch of hands shoot up on that one. I only see one, unless he has both his hands up. Patricia, why?
We don't usually know what is in register 0.
Okay, well, what are you telling me?
I mean, from what I'm reading in my notes, register 1 generally contains 0, but
That's right. This is not always set to 0. However, register 1 is normally, because C and C++ set it that way. And we're going to do what they do so that it makes our interactions with that main program we have a little more smooth. Common mistake. Watch that on a true-false question sometime. Register 0 is not this one. We even fooled one person by saying, why is register 7 always set to a 7? And he had some exotic answer about why that was the case, which of course it's not. Okay, let me look here and see if there was anything else on the list of things that you need to know off the top of your head, which I believe some of you may have left the top of your head elsewhere. Okay. Is the stack pre or post decrement when pushing? Nasu?
It's a post.
Okay. What's the initial address, the actual variable, not variable name, but macro name we should use to determine where the top of RAM is?
The top of the stack is like 8FF, I guess.
Right, it's 8FF. What's that called inside the header file?
Is it yes RAM?
No. Scott, what do you think?
RAM end.
RAM end, yeah. Okay, that's good to know, and I keep that around somewhere. Okay, with some registers, when they have a high and a low piece part, meaning they're 16 bits, order matters. I can go down here, I may not be able to. Where do we do if we want to read? We want to read a 16-bit register. What's the order? Robert?
We read low then high.
Right. And the opposite if we're going to write to the 16-bit register. Anybody remember? I very briefly said why that was the case. Scott, why?
Kind of a guess because we're using little endian as our convention.
Well, not exactly in this case, but yes, we are using a little endian. Dante?
I was going to guess the same thing, that it was because it was little endian.
Okay. Well, the reason is because the high register is actually a shared register. It's used by several components. Not all the 16-bit components use it, but the ones that do, they basically don't want all of your 16-bit to be read in parts. So if we read the low and then read the high, so we're reading in that order, what will happen is the 16 bits won't be available till after the high is read, and nobody else in the middle there could have gotten in and changed that register on us in a way that would harm the read we're getting ready to do, as long as we follow that on all of the registers. You can read the details. Now I'm going to leave you to look up the details because you should be moving around the data sheet. But let me show you where you would find that, assuming I can find it. Do I have a window open here? I do. Let's say, for example, we were using the timer we were using the other day, which is a 16-bit timer with PWM. If we open it up, about the third or fourth item down is accessing 16-bit registers. Here's the details of why. Here's the one that tells us it's not all of them that matter because we're not using the temporary register on some of the others. But very specifically then spells out to do a 16-bit write, do this. To do a 16-bit read, do that. So you should never miss that question again because you can find it very quickly in the data sheet if you need be. And this is worth reading, particularly with registers like a timer where you're sharing that in a way that you could cause yourself all sorts of problems if you did them out of order. Because remember, a 16-bit value is not complete until you've read both those registers. It's very, very important that one of them hasn't been changed on you in advance. We'll also see that some of the registers are buffered in a way that you can actually write to them, but they're not used until we get to the, for example, the next clock tick, or we get to the top of the clock, that sort of thing, or an overflow. So there is some details that we kind of glossed over, but you should nevertheless, when working with a timer, read the data on the timer. Okay. A couple more questions, and we shall get on. It does feel like I'm doing dental work today, though. Some of you guys did not come prepared. If the data direction register is set to read, what does writing the pin do? And let's say we'll put a specific, we're writing a 0. What's going to be the net effect of doing that? Matthew?
So setting DD to read, that's data direction, and then writing 0 would set it to input?
Oh, we're not. We're going to the pin, remember?
Oh, yeah, the
So
pin.
what does writing to the pin do?
I'm drawing a blank currently.
Miguel?
Sets the pin to input mode.
Well, that's what this did. Okay. Robert?
So for writing a 0, we're going to do nothing. If we're writing a 1, we're going to toggle the pin.
That's exactly right. So the 0 causes the actual pin to not change at all. Nothing changed. If this had been a 1, then the output pin would have toggled. There's a difference between the two. If we have the data direction is set to write, and we read port, what happens? Scott?
We will read the output buffer, which will contain whatever was written last time.
That's correct. Okay. Well, it sounds like the people that are going to answer questions know their stuff, and the ones that aren't going to answer are going to just sit there. Okay, let us move ahead a bit. See if we can make some progress. All that was review. That stuff should have been 5 minutes of class time. let me kill this for the moment. Kill that for the moment. Go to your labs folder. Go down to lab 5. Open up lab5.ino and make sure your Arduino is plugged in and that it has the right port number under Tools. And then we're going to look at the code.
I have a question, right?
Sure.
So when I open up my INO file, it doesn't go straight to Arduino, it goes to Notepad++. So
Then you'll have to start Arduino and open it from inside Arduino. All that means is when it got installed, it didn't create a link between the thing. The other thing you could do, if you know exactly where the executable is, you can right-click on an INO file, and it'll have as an option somewhere under it, open as, and there's a box you can say check open as always, and you're going to always open it using Arduino, but you have to search and know where the executable is. So it's probably easier just to open Arduino up and just navigate to the directory.
all right.
If you want, stick around a little at the end of class and we'll get it working. Okay, let's look at what this does. And what I want to do is just kind of take a general glance without reading the code very thoroughly. And then we'll come back and we'll try to understand a little better what's going on. Looks like our code sets the LED on our board to an output and then turns on the LED. Let's turn off the LED. Change that S there to a C. It doesn't need to be on. Now we're going to load into register 16 the number 0, and we're going to store it in a variable called value, which we defined up here as a byte containing a 0 initially, but we're going to initialize it to a 0 as well. Then we're going to load 16 with a 0 again. These could be different values, is why we're doing multiple times. If we were optimizing, we'd take the second one out. But we don't want to write assembly optimized. You want to write it, determine if you need optimization, then optimize. Premature optimization is one of the worst things you can do in assembly code. And way, way, way too many people do it. Now we're going to go to timer control, our timer counter control register 0 on the A side. And we're going to clear all the bytes that are there. We'll come back and look at that in a few minutes. We're going to reset 16 to a 0. It's been a 0 all along. We're going to store that at the counter 0's current count. Now we're going to set a 1 into the timer output interrupt enable for the 0th timer. And we're going to put that, store it from 16 into the timer's mask. I don't remember what that stands. Well, remind me in a while to look up what the name of that is. I'm saying timer mask, but I could be wrong. But it's where the interrupt flag is, which means interrupts would occur if and only if we turn on the system interrupts, which we immediately do. Now we're going to load register 16 with some prescaler bits. 101, we'll have to look up to see how long that is. And then we store that in the timer counter control register 0 B side. Actually, this is the B register that was A. It's not the sides because we're not using the comparator. Once we've done that, we're just going to jump forever. So other than setting things up and getting the timer running, we're not doing much. So we must be doing something in the timer interrupt that's interesting. So here is our timer interrupt. We're going to get the contents of the status register and put them into register 2. Pushing register 2 on the stack. That's so that none of these flags get changed in here. We're going to restore that when we get done by popping register 2 and putting it back in the status register before we return and re-enable the interrupts. Remember, as soon as the interrupt occurred, interrupts globally were turned off. Now we're going to push registers 16 and 17 on the stack. So basically, we're going to save their contents. So in case they had valuable stuff in them, us using them won't hurt anything. At the end, we should be popping them off. So right here, we pop 17 and then 16 before we do 2, which makes sense because we pushed them on in the opposite order. 2, 16, 17. We pop them off, 17, 16, 2. Now we're going to load register 16 with the value that we had in the data section. We're going to store, or we're not going to store, we're going to load register 17 with that increment value we had above, which was a 1. Now we're going to take and add to register 16 whatever value is in 16 is going to be added to register 17. We're then going to look and see if the top bit, the left bit, is turned on. If it is, we're going to jump down here to what's called flip it. If it's not, we're going to load the increment again, add it to 16, and store it at the value. Meaning that out of 126, or out of 256 times that we get called, we're going to look to see, are we at the 128th call? If we are, we're going to do something. If we're not, we're going to flip the bit. Meaning that we're going to count, once the pre-scaler has been taken into effect, we're going to allow this interrupt to occur 128 times without doing anything. So it's going to extend the amount of time between updates. If, however, we don't flip the bit, we're going to increment the value and store it at register 16, and then jump to continue. Otherwise, we're going to negate the value and store it wherever increment is, meaning the 1 now becomes a -1. Now, assuming we've done all that, we're going to get to continue. Now, the purpose for this is we want to count up for a while, and then we want to count down for a while. We're using the leftmost bit, wherever it is there, to determine when we switch the direction we're going to do our counting. Once we get to continue, we're going to store register 16 at value and the value we have so that it's always a positive number and it's always going to be, you know, 100, less than 128. Now, we have a method called 2hex, which is in one of the utility packages we haven't looked at yet. But basically, it takes whatever's in register 16 and turns it into two ASCII characters, one of which is in register 16, the other one of which is in register 17. So when we come back, we can call this method knowing that whatever's in register 16 is going to get displayed. Then if we put 17 into 16 and call it again, we'll print out whatever's in register 17, which would be the right half of the two nibbles we got 2 hex turning us into. Then we'll simply put a new line into register 16, and we'll call send one more time. So just assuming for a second that at this point value contained the number 23, we would run it through 2 hex. 2 hex would put a 3-2 in register 16, and we'll put a 3-3 in register 17. We would then print them out. We do 16, which is a 3 in ASCII, so it would print out a 3. We'd then take whatever's in register 17, which is this, put it in 16 and print that out. So we'd get a 3 printed out. So we would have printed a 2 in ASCII, a 3 in ASCII, and then we load 16 with a new line so that it also gets printed. We then restore everything. So if we run this, actually we need to load it, so we can load it into our device. And you look at your device, you should see that our light is off, but the light next to it is on pretty solid. That's one of the lights on our box, which is, remember, we're sending data, and we're sending it almost constantly. To see what we're sending, we can go to Tools, Serial Monitor, and if you look at that, you'll see that we're printing numbers that seem to be going up and going down. Where it says auto scroll there, see if you can catch the point in time just when it starts to do 7s. And you scroll up a little bit. You'll see it did 5, 6. Here comes our 6s. 7, 0, 7, 1, all the way up to 7F, 7E, 7D. It started down now. So as soon as it got to 7F, it redid 7F and it starts counting down until it gets to 0. So turn auto scroll on again and try to catch it where roughly where 0 is. Once it got down to 0, it starts back up with counting again. So basically we're producing a stream of numbers. This is of course hex we're looking at here, but these are the ASCII characters we printed, each followed by a new line. So internally this was actually just 8 bits. Right here we know it's 16 bits because 0 is an ASCII 0, which is 30. A, we know, is a 41 in ASCII. It's capital A. So along with that, it seems like it would be useful to use this data perhaps in a processing program to be able to look at it. So I'm going to turn my auto scroll back on so it'll continue scrolling. But I'm going to close the monitor. Make sure you close it. Then I'm going to go under Labs into the Lab 5P folder. I'm going to open up 5p.pda. Now I should be able to run this. You should get the COS231 gauge. And as it's going and counting from 0 to 127, the gauge is showing you the numbers from 0 to 100. So if this was on my boiler, I'd be ready to run into the other room because it looks like the thing's getting ready to blow. So all the processing program is doing is it's receiving those numbers, it's converting them, mapping them to a value from 0 to 100, and then it's mapping them so that it hits whatever number of degrees it would be if you rotated it around this point in the center of the dial. Everybody give me a green circle if you kind of understand what's going on. This would be extremely useful if you had a device that was really monitoring something. Like if it was monitoring the temperature in your house, wouldn't you be worried about now? I know I would if it was going from 0 to 100. Particularly if that was Celsius. That'd be from freezing to boiling. Okay, well, let's take a quick look in the processing folder. In the data area here, under processing, anything that is a file you're going to use goes in the data folder. That can't be named images or anything else fancy. It's always called data. In here, we have two images. One is an image of the gauge itself. The other is an image of the needle. So apparently we're drawing this, and then we're drawing the needle rotated somewhere on top of it. I mean, I think I can deduce what's going to happen here. So before we go through it together, and notice down here in the little window is also printing out the numbers it was receiving. But why don't you take and run your eyeballs over this and see if you can kind of figure out yourself before I start talking about it, what's going on in the code. So let's take about 2 or 3 minutes. I'm going to turn my mic off so I can drink some coffee here and slurpy noises. Remember, by the way, if that didn't work, it could be you still had your serial monitor open, or it could be that you have the wrong index number here. Remember, that has to be the index of your COM port based on that other program we ran, and you wrote down that number. So in most cases, it's 0, but not in everybody's case, as I recall. Okay, study that real quick. I'm going to ask random people things about it. Okay, there's not that much code there. Does anybody want to volunteer to tell me what's going on? Okay, Scott, why don't you start out telling me what's in the setup function? Actually, tell me what's above the setup function. What are these things up here for? Why do I have all that?
To process the data coming, the serial data coming out of the board, we need to import the processing.serial header, and we need to initialize variables for the text value that's coming out of the serial. We need a variable to refer to the serial object on which is our board, effectively our board output. And we're going to need image variables for the dial and the needle that show up as our GUI, as it were.
Okay, Dante, why don't you tell me about the setup function?
Okay, so for setup, we initialize the actual size of the GUI, setting to the dimensions.
Well, where do you think I got the 330 by 330?
I don't know. I imagine that's from the actual dials.
Yeah, I just looked at saw how big this was.
Yeah.
And then made it be the same number.
Yeah. Then we load the images into the two P images, the dial and the needle. We create the sensor that will actually be reading from the drive. I'm not 100% sure about the buffer too until, so this is kind of a bit of guesswork, but I imagine it waits some amount of ticks till it actually starts. The sensor will wait like about 10 ticks, and then we set the frame rate to 20.
Right. So this guy right here is a new line character. Okay. And so what we're basically doing is as long as characters are coming in, which would be the 2 digits in our number, which are 1 byte, and then we get a carriage return, or not a carriage return, a new line, it would save it. In our case, we don't care because we want to read each byte anyway. But if it were 3 or 4 bytes of data, we'd want it all at once. So it'll buffer it until it gets this, and then it would move it into the text field for us. So this number is simply wait for this character to occur, then do something. So we'll buffer the data until then we move it into the proper place. Okay, good. You did good on that. Who's next? Who wants to tell me about the draw function? Be one of you two guys again if you want to. Mikhail, you want to tell me about it?
Yeah, all right. So
start with a try. Why am I trying?
The try function, I'm pretty sure that means that it's is that a loop or no? Or you're just testing out data? I don't know what that is.
Well, try, if you look at the indentation, is paired up with this catch. And this is what you do if you catch it. So what this is basically telling us is, let's run some code, and if there's an error, if the error happens to be a number format exception, print it out. So in case we get some data from our device that's not a number, then we want to have this print out the thing. So we'll see it down here in this window, and we'll detect, oh, so we got the wrong program running on the Arduino perhaps. There's also one thing here I just noticed this is indented 2 places and shouldn't be. This should actually be lined up with the word background. I don't know why we let that slip through. So all of this is indented. So it looks like it's inside a background. It's not. So what does this line do? Translate here.
Okay, so the translate line, I'm pretty sure it puts it in the middle of the window.
Right, that's exactly right.
And then you initialize integer v using an integer %.
Okay, what this is going to do for us is it's going to return back to us an integer because we're parsing whatever was just received in the text field, assuming it's in base 16. Remember I told you this is the base 16 number we have. So when we're done, the actual number it parsed is right there.
Okay, yeah. And
Now what are we
next
doing, Joe?
we initialize the float integer, or not float variable, and that's v divided by 2.56.
Why do you think we're doing that?
So think we use VV as the okay, no, I'm not really sure on that one.
Okay, well, 256 looks suspiciously like the number 256. So what this is doing is it's taking V, which ranges from 0 to 256, and turning it into where it is in the numbers proportionally for that. So VV is what portion of 256 is our number. We then double that, and we have some special handling if V happens to be less than 10. And if it's not less than 10, we do this. We had to figure out where the value is, because if we were to look at the gauge, we'll see that something kind of weird happens. Let me go see if I can find it again. Do you notice if this is 20 and this is 10, the distance down to 0 is not the same. The distance from 10 down to 0 is going to be a different value than between any of the other. Let's go up by 10. So the math we have to do in order to point at the correct number down here is different between 0 and, I guess, just 5. But we might calculate to 10. I don't remember. But certainly to here is a different value, because 1, 2, and 3, and 4 all have to fit in that little slice. Whereas in this slice up here, only 21, 22, 23, they got a lot more space to cover. So where are we? Not this. It's this. So in here, we're doing some calculations to make sure when we're in the range less than 10, we can compute where the arrow needs to point more accurately. If it's greater than 10, then there's a standard formula for that. So what do you think this is doing right here?
That rotates the dial VV amount of radius.
Okay, but it's really not rotating the dial, it's rotating the needle.
Yeah, the needle, my fault.
Okay. And then what do we do?
Then you reverse the direction it goes in. Or the
what does this translate? It looks like we were at the center of the screen. So we're going somewhere else.
So you're going back towards the edges?
Yeah, we're going back to the end, because the image of the needle, we can't use the center, because the center of the needle is not where the center of the screen should be. By pushing it this distance will cause this guy to wind up in the right place. We look at our needle graphic, wherever that is. Oh, I can't find that. There. It's in the center of this box. So if we tried to place this at the corner, it wouldn't point to the right spot. So we've got to make sure it and the center of this, I guess that's open somewhere else, but the center of this match up with each other. And we had already translated, we already translated one time here in order to do our calculations.
So
one last thing is what happened.
Okay.
Excuse me?
No, you go first.
Okay, so when we do the image of the needle and we go 0, 0 on it, we want to make sure that the center of the needle winds up in the center of the screen. Serial event. Tell me about somebody else tell me about that. I think we worked them hard enough. What happens in serial event? When you spill your Cheerios? Scott, what happens here?
All right, this is a code that I think is just going to respond to inputs coming from the serial device from our board. It's basically an event, what we might call an event handler.
Right, that's exactly right.
So first thing we want to do is set up a buffer, which is going to temporarily hold the data coming in from the sensor. And looking at the size of that array, it looks like the sensor is able to tell us how many bytes of data are available. Maybe we want to have 2 additional bytes of headroom on there. And
Yeah, do you remember earlier on we said that we wanted it to buffer till it got to a 1-0? We want to allow enough space for all the data it sees before the 1-0, plus the 1-0, plus perhaps it may have a trailing 0 if it's not an even number of bytes or something like that. So +2 seemed to be the magic number. Now we can actually get the number because we know it ends in a 10. And what are we going to do with that line?
Right. So we'll guessing we're going to read the first 10 bytes and store them in the buffer.
Not remember, this is a new line. You're going to read until you find the new line.
Okay. Yeah. All right. So we'll read out of the sensor till we hit the new line character,
Which we know is there because remember up here we said that it had to have one where we buffer until we get to a new line.
Right. So the buffer's filled. We're going to create a new string stored in text out of the byte data that's stored in the buffer.
Right.
And we're going to then basically chop off the new line character, which I think will be in the buffer. Wait, will it?
Yeah, well, it's going to be whatever was trailing over here.
Yeah,
So
okay.
we got to think plus the 2. We know we only have 2 characters we're interested in, right?
Right. So we just want to
Because
grab the
it's
first 2
hex
characters.
digits. Yeah, and print them here.
Yep.
We said print line, so we get a free new line here. But remember when we were printing them from inside of the Arduino, we also stuck a new line on the end of each number we sent, which guarantees this guy's going to see a new line when he's buffering. So this is fairly complex code, but you talked about it like it was an old friend. Robert, do you have a comment? Okay, so that's pretty straightforward on as far as what we would do in order to be able to run this, and run it again one more time, just verify it's kind of doing what we think it should do. Initially, when it starts, you may get a couple seconds when it doesn't have the needle on it yet. I can't show you that because by the time I move it to the screen, it has it. And we made our thing 330 by 330. My guess is, and I'm guessing, is that if we go look at this guy, and we find his properties here. And does he show us? Yeah, it's 330 by 330. So if we were to change our gauge, we'd have to adjust for that. And my guess is we probably made the needle the same size so that it's easier to put on the screen. Because if you write the needle from the start corner, its center point is always going to be the center of this. And so if you rotate this first before you move it, then you have to make sure you're rotating around that point so that when you do move it later from this corner and just write it over this, it'll wind up, because everything else on this is transparent. The only thing if we would look at the needle, you can't see it here, but all of this background is really transparent. That's why it's a PNG file, is because it can maintain transparency. But as long as I rotate it while it's in the center, if I'm rotating around the center, then it will rotate around the center. But then I can draw it from here, the whole thing, left to right and top and down, and this will wind up in the center, also rotated. Anybody have any other questions about particularly the processing part of that. I think the people that did their explanations did a very nice job. Mikhail, do you have a question?
Okay, so in my code, like my Arduino is not on port 0, it's on port 11.
Right,
But
then you have to change this number.
Okay, yeah, I did that, and it says that it gave me an error.
What was the error?
Let me see. It said out of bounds, I think. Yeah, out of bounds. So
okay, what you'll need to do is you need to go back and run that original processing program. It's possible that you were plugged in a different set of devices on your computer or something, and this number has changed. So you just go rerun that. It'll tell you what number you need to have here. And then when you change this, it'll be correct.
So just run it.
We'll run the original one. I forget what number it was. I don't have a window open with it in it right now. It was like lab something else. It has a P on the end of it. So if you look at the labs, well, let me open a window there. It would be labs 4P.
Okay.
If you run that, it should give you a list down here in this bottom window of where all your devices are hooked. You need to find the one that is the Arduino and then figure out what number it is and use that number. Okay, I want to go back to the code. Do I have that open? I do. I want to take a look at the util.s code. We haven't talked about this yet, but this is the code that takes whatever's in register 16 and converts it into 2 ASCII characters. Okay, so when you call this, it's expecting to have register 16 containing a 2-digit, or not 2-digit, well, it's 2-digit number, 2 hidden nibbles. Because it's going to take each of those 4 bits and turn them into a character. Actually, let me use a blackboard here. So let's assume for a second that I have the number hex 35. We know in binary that's 0011 0101. A 3 and a 5. What's the decimal value of this? Scott?
53.
Okay. So it's going to be 48 plus 5. But we're dealing with this. What we want to do is we want to see this number. But if we printed out 35, all we do is print out the number 5. Instead, we want to take the 3, turn it into an ASCII character. We want to take this and turn it into an ASCII character. So initially, this number is in register 16. We're going to take and convert the first part into ASCII and store it in register 16 when we return. We're going to take the second part and store it in register 17 when we return it. That way the guy that gets it can do something with the ASCII characters that represented the 2 ASCII nibbles that are in our original number. So first thing we're going to do is take the number we have and put it on the stack. So we have a 35. Here's the stack. We don't know what else is on it. We actually do. We know that the address above us is the return address of the function that called us. I'm going to write it down because the addresses go down, but think of the top of the stack as being lower. So we're going to put register 16 on the stack, which is a 35 or 35. And just so we remember, that came out of register 16 initially. Now, what are we going to do? First of all, we want to deal with the left-hand side. But before we can do that, we want to extract the right-hand side and deal with it. So to do that, if we AND what's in register 16 right now, remember this is in register 16, with F's, the only thing register 16, we'll keep a track, a log over here, what's in register 16. We had a 3-5. We AND it. That's going to leave us with a 0-5. Now we're going to compare it against a 10. Because if this number is bigger than 10, like 11, 12, 13, or 14, or 15, which are hex digits, we have to deal with those numbers differently because, for one thing, they're alphabetic characters. They're not numeric characters. So if it's greater than 10, we're going to jump to letter. Ours is not, so we're going to OR it with a 30. So in this case, we're going to get a 3-5. Probably shouldn't have started with a 3-5 because it'll be a little more confusing. But I'm going to now take this and put it over in register 17. Register 17 now contains the ASCII character for the 5. So now let's do the high bytes. First thing we have to do is, because 16 has theoretically the wrong number in it, it is the correct number now just by chance, but we need to pop off of the stack this number. Now we need to left shift. I'm sorry, not left shift. We need to logically shift right the register 4 times. It's a logical shift right. Logical means don't bring any sign bits in, but when we're done with that, we're going to have a 0-3 in register 16. We're going to compare it against a 10, because if it's greater than 10, it must have been a letter. We go to letter. If it's not, we're simply going to OR in a 30. We're going to get a 33. Now we're done. When we return, register 16 contains the left half. Register 17 contains the right half. Let's do it again. Let's change the number we have. Let's make the number this time be a BA. So follow the process we have here. BA is in register 16. Again, we'll use this as a notation place where register 16 can be maintained. Register 17 will be over here. And our stack has our return address on it. First thing we do is we push the whole number BA onto the stack. So let's move our stack where we can see it. Here's the stack. It has a return address, but we're going to push a BA on it. Now we need to isolate the right-hand half. So we're going to AND it with a 0F. which means when we're done, that's going to have a 0A in it. We compare that against an A to see if it's greater or equal. It is. So we need a letter. First thing we do is we subtract away from what's in there the number 9. So that leaves us with an 01. We now OR that with a 40. That gives us a 41. 41 is the letter A, so we move it to 17. We now pop off 16 again, which contains a BA. It's no longer on the stack. We shift it to the right 4 bits, so when we're done, we have a 0B. We compare it against an A. It is bigger, so we jump to letter. We need to subtract the number 9 from 11. That gives us a 2. We then OR in a 4, so we get a 42. We can return, because this is the letter B, this is the letter A. The letter B is in register 16, the letter A is in register 17. So when we return, we pop off the return address, and the guy getting it back now has what he had originally in 16 as a single byte spread across registers 16 and 17 as 2 separate ASCII bytes. Robert, you have a question?
Yeah, I noticed something interesting about the logically shift right. So with our experience with the SAP2, you would expect a shift right of BA to end up with AB, because you would expect the A to rotate into the left-hand side. It seems that that doesn't happen with a logical shift.
Right. Shifts and rotates are actually different instructions.
Okay.
And in the SAP 2 or 3, whichever one we did that in, it was using a shift, which was really a rotate. And we always had to, when we were done, mask away the extra bits. But yes, you're exactly right.
So when you...
And we use the logical shift as opposed to an arithmetic shift. We use arithmetic shifts. It would look at the left bit, and if it's a 1, it would, as it shifted, pull 1s in to keep the number negative. So we needed a logical, which always pulls a 0 in on the left. All right, do you have another question?
No, that answered my question. Thank you.
Okay, so that means we should be pretty good at being able to work our way through this code and use this to our advantage. We would then, after we did a 2 hex, give the 16 to the right function, and then we'd take 17, put it in 16, so we could give 16 again to the USART function. And then in our case, we added 1 more byte where we sent the new line along so that it would satisfy the need on the other end to see a new line. Okay, one other thing we could do here we didn't try is let's go back to our code. What do you think is going to happen here if we, instead of saying 1, say 16 for our increment? Let's run that. We'll need to load it on our device. Then make sure processing is closed and open up the serial monitor. You can hit auto scroll down here to stop it. And you can see that it's going by 16s now. What do you think that's going to mean in terms of the dial? Anybody want to take a shot at that? Robert?
It's going to be going much faster.
Well, let's close the serial monitor. Let's open up the processing and run it and see what happens. I have to find my labs folder somewhere. I guess I don't have it open. I'm doing too tidy. Make sure your serial monitor is closed, and then you can run this. I don't know, but I think that might give me a nosebleed. Minotti, you have a comment?
Oh, I'm sorry. I just left my hand up. Sorry.
That's okay. Okay, what if we wanted to try to slow this down a little bit? Where would we look first to be able to see if we could slow it down? Jay?
Do we increase it on the serial event?
No, probably not the best place for it. Scott?
I would take the easy approach of messing with the prescaler.
Let's see if we can do that. Let's first of all close this. I'm going to close processing altogether so we can test in the serial monitor. But let's get our code and let's look at the prescaler code, which we said was here. Where do we find the documentation? Which page in the manual are we going to find the documentation for those bits? Where am I going to look in here? Somebody give me a page number. Robert?
That was a phantom hand. I'm still looking.
That was a phantom hand. It was very phantom-like. Samir?
Is it page 90?
Take a look and see. Probably if you have the same page 90 as me, no. Well, which counter are we actually using? We're using our timer 0, right? So we need to find that first. Here's the 8-bit timer, counter 0. Open that up. Remember, the last entry is always going to be the registers. Open that up. If you want, just go to that page. Then you can scroll forward. We know that the register that was being changed here is register B. So we can scroll down, or we can look over here and find register B. It's here. So here's the CS bits on the right. So their definitions have to be in the next page or so. Here we go. So the best we can do with the prescaler is 101. That's the slowest we can make the clock. So what does that tell us? Robert?
We can't slow this down from the clock, so we have to change it with the increment.
Well, we've already changed the increment. We said we want to see every 16. So we need it to run more slowly. Samir, well, what do you think? What do you think we should do?
Could you like increase a buffer to like maybe possibly slow it down? Like buffer longer, more than like 10 seconds.
But I don't think that's going to be the answer for our problem right now.
Okay.
Robert, your hand up, or is that accidental?
No, that's for real. Could we decrease the baud rate?
Well, that slows down how fast we can write. That doesn't slow down how fast the timer is going to pop. We're actually running right on the edge of being acceptable with these writes in here, because they're actually slowing the interrupt down. In theory, we could back the interrupts up in such a way that we weren't getting a regular updating. So it's generally bad practice to put something like this in an interrupt routine. We're doing it here because this is just sample code. But in real life, we'd never write to the USART while we're inside an interrupt. So that's probably not going to be the best place for us to put it. I can kind of think of two things we could do. One would be we could use timer 1 instead of timer 0 because we can make it count a lot further. The other thing is we could slow the system clock down. If we slowed the system clock down from 16 megahertz down to 1 megahertz, the thing would run 16 times more slowly, which already means we would meet our increment goal. But what would we have to be concerned about if we did that? Robert, what would we be concerned with?
This is just a guess, but maybe that we're not operating at the same speed as what's listening to us.
Well, that could be a concern, except for we want to run at 9600. And as long as we're running 9600, we'd be fine. But that's right on to where we should be looking. In the USART init file, you remember back here when we gave the CF, what was that dependent on? Robert?
I'm sorry, all I see there is an ace of diamonds.
You see an ace of diamonds. Oh, yeah. What about CF? Scott?
This is a parameter that's partially dependent on our clock speed of 16 megahertz.
Absolutely. It's totally dependent on it because it's the amount it's going to count in that time in order to get us 9600 baud. So yeah, we would have to go back and refix these numbers if we change the processor speed. The other thing is we don't really right now know how to change the processor speed. So our best bet would be if we were going to be making this and needed to be able to do that, we would change the timer we're using to timer 1. We'd make sure that the overflow occurred much later. We can count all the way up to 65,536 instead of 256 with a 16-bit timer. And so we most likely would be able to handle our division by 16. Now, if all we were going to do here is change this to let's divide by 2, let's load that and take a look at the dial. It'll run faster, but let's see if it's tolerable. Again, we could probably best place to look is inside processing. Make sure your serial monitor is closed, which I don't know if mine is or not. If it's not, I'll get an error when I do that. I got a dial. It's running twice as fast. But at least we know we could fix it if we needed to. Okay, any other questions about this? Samir?
Could you change the mode of operation?
Not really, because we still want it to do the maximum, and the maximum mode is when it overflows. We could make it compare against another number, which would have it happen sooner, but we really don't want to do that. We want it to happen less often. Okay, let's close that. I'm going to clean all my windows up for a second here. I got too many things open. Yeah, I can leave that. And I'm going to leave that for a second and just do that so I'm back to almost square one. I don't need these two images open at the moment. Okay, let's create another program which is going to run with this. I'm going to open some of the things I just had closed again, but you can do these with me. So inside of here, let's create a new, well, actually, let's do this. Copy lab 5P. Paste it back into the main folder here. rename it so that it is Lab 8P. Now, although we're not going to have to make any changes to it, it might be simpler if we copy Lab 5, paste it in, and I'm going to rename it to Lab 8. Okay, so when I'm done, I basically have Lab 8 and Lab 8P, which are identical to Lab 5 and 5P. Go into Lab 8, rename its INO file to lab8.ino. And open it. Now go to the code and change the increment back to 1 and save it. Actually, let's actually load it onto our device. And run the serial monitor just to verify that it's actually running and that the numbers are 1 by 1. Yeah, okay. And then close that and close the process or the Arduino. It's loaded on your board. It's running. Okay, go into the Lab 8P folder, rename it to lab8p.pda. Okay, now go to the lessons page inside of Blackboard. And you should find a file called meter.zip. Get that, put it on your desktop and unzip it. And then take the file that's inside of it and put it in the data folder. Did everybody get that done? Okay. Now, if we open this up in, just Paint or whatever, you'll see you have 2 pictures of a meter. There's only 1 meter here, but there's 2 pictures of it. The one on the left has all the segments turned off. The one on the right has all the segments turned on. Now, the way this would be used is like this. We'd have a single meter, and I forget what the value is. This is something like 138 out of 256. You would turn on from the bottom as many segments as are necessary to demonstrate what portion of the numbers you counted. So it starts out with nothing on, first one comes on, second one, third, fourth, goes all the way up until you get to the top one turned on, you get to 255, and then starts back down again. So what we need to kind of see would be, this is what you're going to actually display. So the window size would be proportional to this somehow. Let me see if I have the size of that for you so you can write it down. This is 95 pixels wide, 508 tall. This is obviously bigger, so you're not going to display this directly. You're basically going to display the one on the left, and you're going to use the segments from this one to replace the segments from that one as necessary to make it do the right thing. So let's go for let's play around here for a second. Let's go into Lab 8P. I don't think I have that open. So we don't have a dial and a gauge or needle. We have a P image here for a gauge. Which means we don't need to load that guy or that guy, but instead we need to say gauge equals load image. We call it gauge dot thing. And what size did I say we wanted it to be? Somebody remind me.
It was 9558.
5 by 508.
Yeah.
Okay. Now down here somewhere, we're going to get into possible trouble because do we ever use our images anywhere? Here we do something with the image for the needle. And we set the background. Change this to say background gauge. Okay, let me leave that as it was. Copy it and comment out the first one. And clearly down here, we're not going to actually be putting a needle on top of it. So I'm just going to comment that out for now. That may be enough to get a picture. What we want to make sure your number is here, if it should be if the other one worked. And we can actually, we're never loading these, so we can actually comment them out so we get an error if they're supposed to be there. So make sure your serial monitor is closed, and then let's run this. I have to somehow get mine to come move off the other screen, which is going to be tough because I can't grab an edge of it. Did I spell the name wrong?
It's meter.png.
Oh, is it meter? And we really should change it to meter everywhere else. I get them all. I somehow have to, if this ever happens to you, I have a program running, but there's no way to close it. Come up here and hit the stop button, and it'll actually stop the thing that's running. I'm going to try to run it now. So I get the same background image has to be the same as your application. Okay, well, it can't be for now because this is not what we want to print. So really we'll have to create a background that is pretty much clear, and then we'll have to paint the image. So let's try that. Let's change where it says image needle here. I'll leave the old one alone and we'll make meter be here. My guess is we don't need to do some of this, but let's see what happens. Comment out the background here. We can make it something of our choosing later. Ha. I can't grab a hold of it because it's not resizable. Here we go. Is yours doing that? Okay, well, that's pretty cool looking. For now, we know that we don't want to do the rotate or the translate. Probably neither one of the translates. Try it again. I can't grab it. I should have picked a bigger meter side because I'm running into the edge marks. I don't think there's any way I can get that on your screen.
Professor.
Uh-huh.
If you right click on the status bar and then hit move.
Yeah, I did it. There we go. That worked. Mine was grayed out unbelievably. There we go. So this should be what you see. And your mission would be, as these numbers are changing, to fill up the thing, remove it. And you can use the image that's next to it to extract the pixels. So did everybody get that to work, at least at the level we're looking at right now? I mean, it doesn't do the right thing yet. Okay, where did I put the other guy? Remember, this is what it'll look like as it's running. This thing will fill up, go to the top, and then go down and go away. Anybody have any question about what it should look like? Okay, this is a homework assignment for you to be turned in Monday night. You have a week to do this, but I know some of you have other programming assignments and things going on right now. So you could do this when you get home and not have to worry about it, or you can wait till the weekend and, you know, work on it then. Simply modify this program so that what I just told you it should do actually happens. Now, you can't share code, but you can share advice. You can talk to other people about the assignment. Just don't do like you did last time and copy code. You know, those of you that did that, shame on you. You're some of the same people that don't answer questions when I ask them to you because you don't bother. But, you know, take a good shot at making this work correctly. And I'll give you the extra. Normally this would be due on Wednesday, but I'll give you until Monday because I know some of you have some fairly big programming assignments you're working on at the same time as this. They don't want them to get in the way of each other. Anybody have any questions about this assignment? You do not need to change in any way Lab 8. It's already running. It's on your Arduino. You just need to change the user interface, which is this Lab 8P that we just started creating. The other thing is already doing the right thing in terms of sending you numbers. Anybody have any questions or anybody excited about getting to do a programming assignment? Make sure you save it. I'm not. Actually, yeah, I will. I'll save it. Good. Sargon's excited. I'm glad somebody is. Matthew, you have a question?
Just to reconfirm, you said the bar should reflect 256, or is it out of 100 as
Zero.
well?
It goes, well, the numbers you're getting
Yeah.
go from 0 to 255.
Yes.
So you have to map the 30 bars you have on that meter.
Okay. Thank you.
To that range, whatever the division turns out to be.
Okay.
It won't be the same math that's already there for the last guy because he
Of
was
course.
mapping from 0 to 100, I think.
Mhm.
But
Thank you.
you're still mapping, if you think about it, from 0 to 100%. So that might be useful to know as well. But the numbers you're going to be receiving are still 0, 0 up to FF. Any other questions? That was a good one. Okay, let's talk about another piece of Arduino code we could work on. It's going to be called Lab 7. I don't think you all have a Lab 7 yet, do you? Yeah, I didn't think you did. Okay. This is related to a problem we did earlier in the semester in some ways because some of you used this algorithm in reverse, I think, or a variant of this. It's called Double Dabble. Anybody remember that one on the SAP 2? Well, the idea here is that we have a hex value. So again, it could be anything from 0, 0 to FF. What we want to generate out as a string is a binary coded decimal version of that. Meaning that we want to generate a number that goes from 0 to 255. So it looks like the decimal equivalent. We're going to store it in whatever's necessary to store 255 as bits. So 0, 0, 2, 5, 5 would be the maximum number of bits we need to be able to store 255 as binary coded decimal. Since we have to do things in bytes, that's a byte, and that's half a byte. We also will make use of an empty 4 zeros on the start of it. So if we wanted to see what this ranged from, it would range from 0, 0, 0 up to 2, 50, 5. So if somebody said, I want to take the number C3 and turn that into BCD, what is it? Work that yourself for a second. Pretend like this is a test question. Turn C3 into decimal and then encode it in binary coded decimal. We talked about binary coded decimal for less than 6 seconds, I think, the first night of class, and then again once inside of the SAP 2 lectures. Get your grocery store calculator out if you're having trouble. And when somebody gets C3 converted to decimal, tell me what it is. Scott, what did you get?
195.
Okay, sounds like a highway in New Jersey. So 195, we know it's going to have 4 zeros because it's a 3-digit number. 1, 9, 5. Now, how is that going to be encoded in binary as C3? Well, C3. So our mission is to take and convert from that number to that number. We want to do it using the assembly language on the ATmega 328P. Just told you the algorithm name, which is double dabble. So we should be able to find out how to do that easily enough by looking at the Wikipedia. I think I even have it bookmarked on mine somewhere. Now it works both directions. We're going to work from binary to binary coded decimal. Notice we're not using ASCII here, so if we wanted to print this out, we'd have to turn each of these nibbles into a binary coded number before we were able to print it. And we probably would want to do that because we were transmitting this number, for example, from the Arduino to a processing program or to the serial monitor. We'd have to turn each piece into ASCII so that we could use it. Okay, so let's look at double dabble here. Easiest way to look at it is to show you the algorithm. First of all, I'll show you the storage we're going to use. I'm getting tired of them begging for money. Not sure we can get rid of that. So if the number in hex looks like that, when the algorithm is over, we want all of these changed to zeros, and we want the number to be the actual value that it is. So this is an F3, which we know is the number 243. So we'd expect to find a 2, a 4, and a 3. So we, of course, are going to have 4 more zeros over here because we want it to fit in bytes. So the 4 zeros and this 2 would fit into a single byte, followed by this and another byte. So the algorithm, once we initialize it this way, is we make all of these zeros, put the original number over here, is to be done n times, n being the number of bits we have to translate, in this case 8. We're going to look at each binary coded digit in turn, and we're going to determine whether or not it is 5 or bigger. If it is 5 or bigger, we're going to add 3 to that nibble, and then we're going to left shift everything 1 bit. Otherwise, we're just going to left shift it 1 bit. I'm not going to tell you the math. That's for you to enjoy on your own or talk to a math teacher about and see if they can explain it to you. Good luck with that. But it's basically taking care of the carry that we would be omitting. So here's a number being converted. Let me make that a little smaller. Yeah. We have our initial number, all zeros on the left. Nothing in this is bigger than 5, so we simply left shift. The one that was here is here now. We bring in zeros on the right. Nothing is bigger than 5, so we shift again. We shift again, but this time we have a number that's bigger than 5. It's the number 7. So we add 3, making it a 10. And then we shift again. This number is now a 5. We add 3 to it, giving us an 8. Then we shift again. We shift again. This number now is a 6. 6 is bigger than 5. So we add 3. But this time we're adding it to the tens position, not the ones position. That means now we have a 9 over here. We need to shift again and shift 1 more time. When we're all done, we have a 2, 4, 3, which is the answer in binary coded decimal that we wanted to have. So the algorithm is pretty brute force, pretty straightforward. There's 8 shifts. Every time we shift, we have to look to see if any of the parts have gotten 5 or bigger. If they do, before we shift again, we have to add 3. That's all that happens. We know the last guy because the biggest he can ever become, if it could only be 8 bits, would be 255. We never have to check this guy for 5 because he's never going to be bigger. He'll always be 2, 1, or 0. Anybody have any questions about that process that's here? Why don't you take and kind of sketch out a plan of attack for this? Given any arbitrary number, write some pseudocode. This doesn't have to be real and doesn't have to be code that anybody else would even recognize this code. But let's write some pseudocode which will do that algorithm. And specifically this, there's a version down here of the same thing just with more bits. We're always only going to be doing it following this pattern. But at different times, different things in the 1s or the 10s column will be 5 or greater. So where the adds happen are dependent on the actual value of this number. So trying to use some pseudocode. And if you want to, if you have time to think about it, let's take the number 0110100 as the number we want to convert. That's the hex number 64. So it'll go in the right-hand half, and then we do the algorithm on it using your pseudocode and see if you get the right answer. Just take a shot at it. For a while, you might want to bookmark this page. It was just the Wikipedia's version of Double Dabble. Let me write it in big. Somebody probably already put it in the chat, but in case they didn't, that's where you want to go. So think about it. Challenge yourself to get it right. Okay, who wants to tell me what the first thing I have to do is? Mikhail?
Put down all zeros and then put down 64 next to it.
Okay. I'm only going to use 3 digits here, even though we probably internally will use 4. And then we need our 64. And while you're still on there, what's the very first thing I'm going to do?
Since the ones is 0, you shift it 1 left. So then.
Okay. So what number am I going to have in here now?
So hundreds would be 0, tens would be 0, ones would be 0. And now your number,
everything stays zeros, right?
Yeah, now your number is 1100 1000.
Exactly right. Okay, somebody else jump in now. What's the next thing I'm going to do? That's who?
So you're gonna put like 0, 0, 0, 0 on the 100 place.
Oh, conceptually, what am I doing now?
So
I did an initialization. This was a knit. This was a shift. And what's the next thing I do?
Oh, so you shift it again.
Well, we first of all check to see if we have to do anything with these numbers. Check it, check it, check it. None of these are bigger than 5, so we don't have to add 3. So we'll do another shift. So what numbers do I write down here?
It's gonna be all 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 1, and another 1, 0, 0, 1, and 0, 0, 0, 0.
And that was a shift. Okay, what happens next? Somebody else get on there and answer for me. Robert?
So we'll look through our three nibbles that we have. None of them are bigger than 5. We're just going to shift left once, which will leave us with all zeros except for the second bit of, just like that. And then 0, sorry, 1, then 0, 0, 1, followed by zeros.
Which was a shift. Okay, what do we do next? Somebody else jump on there. Mohammed?
Since it is still less than 5, so we also shift.
Okay.
So
what numbers am I typing?
Zeros, all zeros for the first 4. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0. And then it is 0, 1, 0, and then 0, 1, 0, 0, all zeros then.
Okay. Matthew, what do I do now?
Since you have a number greater than 5, you're gonna add 3 to the ones, which means it will be 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1.
6 and 3 is 9, right?
Oh, yes, that is correct, actually. So there's a 1 at the end.
This hasn't done any. These stay the same. What did we just call it? What did they call it on this chart over here?
They just said
add. Okay.
Add 3 to ones.
Yeah. Okay, now we need to do the shift. So tell me what the shift is.
It's 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0 till the end.
Okay, who's next? Dante?
So first we're going to check to see if any number is bigger than 5. And then after we realize that none of the numbers are bigger than 5, we're going to just shift everything left.
Okay.
So it'd be,
So we're shifted.
so it'd be 0, 0, 0. So 4 zeros. 0, 0, 1, 0. 0, 1, 0, 1. Little zeros left in there.
Okay. We've done 6 shifts so far. What's the next step that has to happen? Scott?
Yeah, we're definitely not done.
What do we always do if the number is bigger than 5?
If the number's bigger than 5 in a tens, hundreds, or ones, tens, or hundreds, we've got to add 3 to it.
This needs 3,
That
so
needs 3, so that's 5 plus 3, that's 1, 0, 0, 0.
and then these are all zeros over here.
Yep.
And this would add 3. We need a shift now.
Right, so 0, 0, 0, 0, 0, 1, 0, 1, and then 0, 0, 0, 0. And zeros in the original.
Okay, now what do we need to do? So I got you. You go ahead and finish this one for me.
We still have a digit greater than or equal to 5 in the 10 spot. So we got to add 3 to it. So we have 0, 0, 0, 0, and then 1, 0, 0, 0 again, all zeros, all zeros, all zeros.
Need one more shift.
One more shift to the right. So we have 0, 0, 0, 1, then all zeros, all zeros, all zeros, all zeros. We do our
That can't be right. We have the number 100. We would do our check, right? But we know we don't have to check the left, and there's no ones in any of these other ones, so there can't be anything bigger than 5. So is it possible that hex 64 is equal to 100 decimal?
That's what the grocery store calculator says.
Well, good for you. You shop at the right store then. Okay, so we just did the algorithm. Now the question would be, can we easily convert that to code? And if we do, is it going to run quick? I mean, what sort of things? Because this would be a useful thing for us to be able to do. So let's look under lessons. And let's see if Professor Bastain was nice to us. Did he give us a lab7.zip? So if you find one, unzip it on your desk and then take the file that's inside it and put it into your project folders. And then let's open that up inside of Arduino. When we load this onto our device, don't forget to load the other one back again when you go to work on that homework, because this will be giving you funny numbers if it works. Well, it thinks it's double dabble. So let's kind of just eyeball through the code here a little bit and see if we see anything that looks familiar to us. Turning off the LED, getting rid of interrupts to make sure that no interrupts occur while we're processing. We leave this out quite often, and we would get an interrupt from the serial port if somebody were to type something. But we don't normally care because all it would do is just reset the chip if you don't have a handler in place. And we have a handler, does nothing, so it would basically not really interfere with us. So You know, probably a best thing to do with this would be, let's run it and open the serial monitor and see if it's printing anything. Load it onto your chip. Remember, we just replaced 8, which you have to put back there before you do your other homework. Go to serial monitor. And let's see, did it print the numbers from 0000 up to 0255? Looks like it did. Give me a green circle if you got that to work. Now, if you reach over next to your USB connector on your board, there's a reset button. Push reset. When you release it, it should do it again. So it's only printing it out once and stopping. I guess we could kind of scroll backwards to see if it looks like we got most of the numbers. So these are definitely decimal numbers, but they're written as binary coded decimal. First nibble, second nibble, that's 1 byte. Here's the second byte, 55, which is nibbles that are both digits or decimal. So we have 4 nibbles, all of which are decimal, and a nibble goes from 0 to 9. We wouldn't have had to print the 0, except I imagine in the code we just simply don't care whether or not, in case we ever wanted to make a number that was 4 digits long. The processing program that we might write to process this could later on throw away leading numbers. Okay, so it looks like, based on the output, we're loading register 18 with a 0. Putting it on the stack so we can get it back later, because we're probably going to clobber it somewhere along the way. Then it looks like we're clearing out 16 and 17. Loading register 19 with an 8. Okay, here I'm going to make some guesses here. That is going to be register 18. That's going to be register 17. And if we add 4 zeros in front of this, in all the lines, oops, I actually put those all in the wrong place, didn't I? Can't fix it right now, but you get the idea. We're going to take the number we're converting, put that in register 18. These will be register 17. These will be register 16. Register 19 contains an 8, which is the number of shifts we're going to have to do with an 8-bit number. Then we're going to loop. We're going to call shift, because initially it's always safe to shift the first time. Then we're going to go through and fix any number that's 5 or greater in all the columns. Decrement 19, so we only have one less time we have to shift. And just do that forever. Once that's done, register 17 gets saved. We then call to hex, which is going to take register 16 and turn it into register 16 and 17. We print 16. We move 17 to 16 and print it. So now we got the first 2 digits. We now get the 17, which we had saved, move it into 16, call to hex to break it into its 2 parts, print them out, and then put a new line on the end of it. When we're done, we can pop 18 off, increment it, and push it back, because we need to know what the value was that we're incrementing. Remember, we're doing every number from 0 to 255. We're saving it on the stack, and the new number gets incremented and put back on the stack, so next time we ask for it, it'll be the next value. Then we come back and do it all again. Eventually, we'll have run out of numbers. We just pop 18 off because we don't need it on the stack, and we just jump here forever. Shift is simple. We do a rotate left of 18, which means the bit we're going to take in on the right is whatever's in carry, which we cleared. Rotate rotates through carry, meaning our left bit went into carry, which we're now going to pick up and rotate into this register, rotating its left bit into carry, which the next guy can pick up and carry, use it, and rotate out the last bit, which we don't need. Then return. So this shifts those three registers for it as though they were a single register. Finally, we do a fix. We're going to compare what's in register 19 to see whether or not we need to fix the ones or the tens, right? Well, I'm sorry, to do, don't do. If 19 at this point contains a 1, there's nothing to do. Otherwise, we can fix the ones and fix the tens. We never have to fix the hundreds. I will let you work your way through how we do the fix, but basically it's going to be compare against 5. If we don't go to done, we add a 3. Same thing here for the tens, but we'll just be pointing at a different spot. But we'll have to left shift them over because they're the ones and the tens are sharing an actual byte. I'll let you figure that out on your own. No point giving you all of the details. So study this. I'm going to ask you, like I did this time, next time I'm going to just call on people to tell me how things work. You can bet that this is going to be some of them I'm going to ask you. So don't go, oh, I didn't know my dog ate my homework, or I forgot, or I didn't write that down. You know, those are not good excuses anymore. Anybody have any questions about this other than what those last couple of methods are doing? And it's very simple to read. Just remember in these last two, because a register is sharing, you know, the tens and the ones, we have to do check for 5 in both parts. But we can't check while it's in the leftmost position. So to check the left part here, we have to shift it over so that when we're checking it, it sits in that position. And then, of course, we have to restore it to the right place when we're done. So you have to check the ones and check the tens, which are sharing, in our case, register, I believe it's 17. No, yeah, I think it's register 17. 16 only contains the hundreds, but they're in this position anyway. And we know they never get bigger than 5. Anybody have any last minute questions? I think we're running a little over time, but that's okay. Get started on your homework if you have the time to do so. But remember, you're going to need to turn it in at the start of class on next. You may have to demo what you did. You may have to show it to the class. And you don't want to be that guy that didn't do it. Okay, any last questions? If not, have a good night, and I'll see you on Wednesday. You too.
Good night, Professor.
Have a nice night, Professor.
Good night.